So this is my volume revolution about the y-axis for the torus, or also known as the donut. So first things first, in order to revolve, and we're doing this with the ring and washer method. And so what you need for that is you're going to need an outside radius and an inside radius, which were found using a dial caliper, because we actually measured the donut with the outside radius being 1.6 centimeters and the inside radius being 1.2 centimeters. So from here, we're going to, I mapped out what it would look like on a two-dimensional plane. So we have our if we were to chop the donut in half, we got like a circle right here. And so for this, because what I'm going to do is I'm going to break this circle up into 4 pieces pretty much, because it's going to make it a lot easier to integrate. And it makes the numbers a lot easier. So inside radius is going to be defined by this portion of the circle, because this is the function, which you'll see how we define it later. And then the outside radius is going to be where the center of the circle, which is right here. You can see right here. So the way we define the inside of the radius is through the circle function equation. So we have 1.2 squared equals x minus 1.6 squared plus y squared, and we're going to get this in terms of y. And what you find is you get a plus or minus the square root of 1.44 minus y squared plus 1.6. And you can see I represented those in different colors here. We have the black being the left side of the circle and the red being the right side of the circle. So from here, what we're going to do is we're going to plug this into our area equation. Pi, pretty much just pi r squared, with the r's being the outside and the inside radius, as I said before. We do that here, and now that we have our area, we're going to want to integrate that by revolving it around an axis, the y-axis in this problem. And that's how we find the volume. So I have that here defined here. And so I plugged in all the values here. And so pretty much, I tried to actually do the integral by hand. It was a very difficult process. Just here's some work of it right now. I got into 3 separate volume integrals. The first and the third were easy because it was just y squared and then negative 1.44 dy. So those are pretty easy, but this second integral here, 3.2 times square root of 1.44 minus y squared dy, was quite difficult. So I did a lot of math over here, did a u sub, just a bunch of different techniques, integration charts, stuff like that. Eventually found the right u substitution, got it into a trig sub pretty much, and did some double angle theorems, and then did another u sub to finally be able to integrate it. And from there, you can this piece right here, you can see was how this is how I defined the this would be the second volume, not the third, the second volume. And yeah, so I used inverse sine, stuff like that. I think it worked out. And so from over here now, you can see that I wrote out the entire integral in terms of y, and I integrated, and not this. What I found was, this was what I found. And so now for the second piece, because using that piece, we got the left side of the circle, and I forgot to mention that we actually I said it before, we only got 1/4 of the circle, and because it's symmetrical, we can just multiply it by 2 to make the constraints of the bounds easier. So we're going to be getting this portion of the circle here with that negative square root equation right here. And so for the second piece, I did the same thing, but now we're going to use the positive x as the outside radius, because you can see that this function is now on the outside of where we want to integrate, while the 1.6 radius is now going to be the inside of the integral, and so or of the radius. So we're going to do the same thing now as we did before. I kind of show it here. You can't really see the process because it's the same thing. It's just the radii are going to be flipped now, and then so I do that here. Get the same answer pretty much. And what I found was the volume of the first the first semicircle there was 15.5 centimeters cubed, and I found that the second volume integral was 29.9778 centimeters cubed. And now I'm going to add them because we're just going to add the volumes. What I found was the total volume of the torus was 45.479 centimeters cubed. So that is how you find the volume of the torus, or also known as the donut.